Welcome to part 3 of our urinary system lecture. In this part, we're going to talk about urine composition. So what should be in our urine by the time it gets excreted and what should not be there. This is going to match page 424, about 3/4 of the way down, where it talks about the characteristics of urine, through page 527 in your text. All right, in last lecture, in part 2, we talked about the 3 steps of urine formation. And we're going to just review those real quickly, not so much how they happen, but what should be left after each of these. So first we have our blood plasma, and it's circulating through our blood. And I've put a picture up here of sort of everything that should be going through our blood vessels. And you can see there's red blood cells, there's white blood cells, these big sort of purpley blob things. There's some platelets and clotting factors that are big proteins. And then we have this yellowish liquid that's the blood plasma, and we know from our circulatory system unit that there's things like ions, very small things like glucose and ions dissolved in that. So relatively, even though we think of cells as very small, these cells are actually really big compared to all the stuff that's dissolved up in this plasma that we can't even see in this picture. About 150 to 180 liters of plasma gets filtered every 24 hours. To put that in perspective, 2 liters is a big soda bottle. So think about how many of those would be filtered through if we're doing 150 or 180. That's about 90 soda bottles worth of blood plasma getting filtered every day. Only about 1 to 1.8, so not even a full soda bottle of that actually ends up being urine. So most of what's filtered actually goes back into our blood. We're only getting rid of the waste that we can't use anymore. So hopefully it's not very much of that. Otherwise we'd be having to make our blood all over again all the time. So we start out with the blood plasma, and step 1, as it reaches the kidneys and it reaches the glomerulus, that little knot of capillaries, is that it's getting forced out by that high pressure. That's called the glomerular filtration. And remember, this was non-selective, so anything that's small enough to go through those little podocytes is going. Okay, it's only based on size. So these red blood cells, these white blood cells, these proteins that are big are not going to be able to fit through. They're going to stay in our blood, but everything in this blood plasma is going to get forced out. Okay? So now we have formed filtrate. So it's basically blood plasma minus those proteins that are too big to filter out. Okay? We don't want to pee out filtrate how it is. There's lots of good stuff in there. There's lots of good ions. There's lots of good glucose. There's lots of good water. We don't want to get rid of it. It's not waste. It just happened to be small enough to go through and get filtered out. We want to reabsorb that good stuff before we pee out the waste. So that's where tubular reabsorption, that second step, comes into play. As it's going through the renal tubule, that first convoluted tube, and then the loop of Henle, and then the second convoluted tube. Remember those peritubular capillaries, that little net of capillaries that's very low pressure, that's got lots of pores, that's really good at reabsorbing, is going to work here. This is selective. Okay, it's based on what we need in our blood. And remember, this is not passive. This needs energy, and it needs those little transporters. Think of our guys standing at the airport waiting for their thing, okay? Little signs with glucose or little signs for amino acids. It needs specific transporters. So this is where we're going to have a lot of transporters for the stuff we want, like glucose, and not so many for the waste products. The last thing that happens is tubular secretion. This is sort of a last adjustment to make sure our acid and base levels are okay. And things like potassium and creatine that might still be in our blood but that we want to excrete as waste get forced into that urine. So by the time urine gets peed out, it no longer looks like the blood plasma here. All the good stuff has been reabsorbed. All the not so great stuff is in it. So it's mostly water. Okay, we pee out hopefully about 1.4 liters a day, assuming we're hydrated. And then we have very small amounts of uric acid, bicarbonate, creatinine, potassium, sodium, chloride, urea, etc. We'll talk about what each of these things are. But those are all waste that our body has decided we don't need anymore. And a lot of these things are the byproducts from our cells just doing their day-to-day business. They're sort of like the trash of our cells. Okay, so what should our urine look like when this is all said and done? It should be mostly water. So even though a lot of the water gets reabsorbed and still used in our body, we should have enough to water down the solutes that are in our urine. Our urine should not be a dark yellow color. That means it's too concentrated. Okay. Specific gravity, I'm sure you've seen before in chemistry and maybe in physical science, is just the density of something compared to pure water. So pure water is going to have a density of 1, or a specific gravity of 1. Urine should have a specific gravity that's just a little bit higher, somewhere between 1.001 if you're very dilute, you're very, very well hydrated, to 1.035 if it's really concentrated. Maybe you're a little dehydrated at that point. Okay, what should be dissolved in this water? The solutes that should be in this water are various ions, so sodium, potassium, and that last one, this one is called bicarbonate, and various others depending on what you have extras of or don't have in your body. Nitrogenous wastes, these are those wastes I was talking about that are the byproducts of our cells doing their job. So urea, uric acid, creatinine, and ammonia are all byproducts from various things that our cells do. So those are waste. Those want to be excreted. Urochrome is actually a protein pigment, and this is what gives the yellow color. It's one of the steps in the breakdown of hemoglobin. So as we're breaking down our old red blood cells, remember that's one of the things the spleen does, and then that is in the blood plasma and it's getting excreted. It's going to turn a yellow color in the process of being broken down. This is the same reason that our bruises eventually will turn that yellowish color before they're done healing, because those red blood cells, the hemoglobin in them is breaking down to urochrome. And the pH of our blood, of our urine should be about 6. So slightly acidic, but remember 7 is neutral, so it shouldn't be really, really acidic. Okay. Urine is really good as a diagnostic tool. First of all, it's easy to get. People pee multiple times a day. Okay, you don't have to stick a needle in them to get blood. Even if somebody is having trouble urinating, you can catheterize them, meaning you can put a tube through their urethra and get urine out. You know, if you go to the doctor and you need a urine sample and you aren't able to pee, they can just have you drink some water and then you'll be able to urinate. So it's very good because it's easy to get without being invasive, but it's also good because our kidney's job is to keep the homeostasis of our blood. So keep that in mind. We're trying to keep our blood even, not our urine even. Okay? And we keep our blood relatively even if we're having changes in our diet. Okay, we don't eat the same thing every day. Maybe we're taking some medicines. Maybe we have different levels of hydration each day. Maybe we're injured. Maybe we're sick. Despite all of these things, our kidneys work to keep the levels in our blood the same. Whatever they have to get rid of in order to keep the blood the same is what ends up in our urine. So by looking at our urine, we know what we have too much of or what we don't have enough of by whether something's in our urine a lot or not there at all. So the presence of something or the absence of something can indicate a problem. For example, if I'm a football player and I get hit really hard in the back and my kidneys get jarred really badly, okay, that might cause some rupturing and it might cause some of those red blood cells, some of those bigger things that shouldn't be able to go through the filtrate to get in there, and then I might see blood in my urine. Okay, another example, if I see a lot of glucose in my urine, this means it's not being absorbed properly. We shouldn't be peeing out glucose. That should be getting reabsorbed and used. But if it can't, that could be a sign that diabetes is going on. So sometimes the first sign of diabetes is from a urine sample. If you look at table 15.1, which is on page 528, it gives you a lot of other examples of finding something in the urine indicating something that's wrong. So that's a good place to look. Okay, and that ends part 3 of our lecture. So hopefully that gave you some idea of how things get into our urine, why they should be there, and what it means if they are there and they shouldn't be, or if they're not there and they should be. Again, you want to take a look at page 524 through 527 in your textbook.